Hello students, so today we are going to start the new lecture series on the uh, mathematical physics. Now there are many topics in mathematical physics. For example, there is matrices and tensor, there is complex differential equations, integrals. So first we'll start with matrices. Now there are different types of matrices, like there is something called an identity matrix, which is nothing but matrices consisting of 0 and 1. So all the diagonal elements are 1 if it is a 2 by 2 matrix, and if it is a 3 by 3 matrix, then it will look like this. So an identity matrix is always a square matrix. You will see the diagonal elements are always equal to 1 or multiples of 1. Maybe if you say this is, we consider this as equal to I2, and if it is I3, so it can be also 2I2. It means 2 into 1 0 0 1, and it is equal to 2 0 0 2. So twice of this identity matrix. So the non-diagonal elements are always equal to 0. Now there is another type of matrix called scalar matrix. Say if it is going to write, just we have given you the example 2 0 0 2, so it is equal to 2 into I2. So a scalar term is being introduced, is being multiplied with this identity matrix, that is called a scalar matrix. Then we have something called a symmetric matrix. A symmetric matrix characterized by Aij is equal to Aji. So it means if A12 will equal to A21, or A23 will be equal to A32, so we can write this matrix in the form like A11, A12, A13. So this should be A21. So since A12 is equal to A21, these two are equal. So let us first write in its usual form: A12, A22, A23, then A31, A32, and A33. Now, so this element and this element should be equal, and this element and this element should be equal, and this element and this element should be equal. So if that is the case, then we can simply replace this three elements by A12, A23 and A13. So this is what is a symmetric matrix. Now if by chance this matrix is characterized by the relation that Aij is equal to minus Abi, that means each of these elements having equal indices are with a negative sign, then the matrix will become a skew symmetric matrix. So there are other different types of matrices. We will take up one by one. So these are the very common matrices. Now suppose we have a case where B, matrix P is equal to inverse of matrix A. So in that case, AB should be equal to I, which is an identity matrix, or which shall also be equal to B into A. And also, if we take AB and perform the inverse of this, so it would be equal to B inverse into A inverse. Now, in this case, if AB, A into B is equal to B into A, then it implies that matrix A commutes with P, and if AB is equal to minus PA, then A anti-commutes with P. Next is what is a transpose of a matrix? A transpose is given as if the transpose of A, we represent it as A dash. So it simply means that we interchange the rows and the columns. That means Aij will now be replaced by Aji, and vice versa. So that means if there is a matrix called, say, 1, 2, 3, 4, 5, 6, 7, 8, 9. So the diagonal elements will be same. If this is equal to A, then A dash will be simply 1, 4, 7, 2, 5, 8, and 3, 6, 9. Further, there are some properties related to transpose. That means if A plus B transpose is equal to A transpose plus B transpose, and A double transpose is equal to A. That is quite obvious. And scalar multiplied by A, and if you transpose it, it is equivalent to K be multiplied by that transpose. So these are some simple properties of transpose of a matrix. Secondly, there is another type of matrix, another property of a matrix called conjugate. Of a matrix. So if the matrix elements are complex numbers, that means then we replace the matrix elements by their conjugate. That means we can call it, if A is a matrix, say given as say 1, 2i, 3, 4i, 5, 6, 7, 8, 9i. So the conjugate as A bar is simply so here these elements are the complex numbers 2i, 4i and 9i. So in the conjugate matrix they will be replaced by the conjugate of these numbers. That means it will be 1 minus 2i one second. Mm, 3 minus 7i plus 5, 6 and 7, 8 minus 9i. So changing the sign of the imaginary part is called the conjugation. Next we have a matrix called Hermitian matrix. That means if the transpose conjugate of the matrix, you transpose it and every conjugate gives you back the original matrix, or in other words, Aij is equal to A Ji bar, then we call this matrix to be Hermitian matrix. And another property of this Hermitian matrix is that the diagonal elements are real in a Hermitian matrix. Next is the orthogonal matrix. So it has to be a square matrix first of all. And it will be called an orthogonal matrix if transpose conjugate into that original matrix gives you the identity matrix, or rather we can say that the transpose conjugate is equal to the inverse. Oh, I'm sorry. This is not the. This is the unitary matrix, not the orthogonal matrix. Cut it down. The unitary matrix. Which an orthogonal matrix when A into A transpose is equal to I. That means A transpose is equal to A inverse. Whereas in unitary it's A transpose conjugate is equal to A inverse. So we can from these we can say that the inverse and the transpose of an orthogonal matrix are orthogonal. We can also say that the product of any two or more orthogonal matrix is orthogonal. So let's try to understand what is the first line means. So it is going to say that the inverse and the transpose of an orthogonal matrix. So if we consider A to be an orthogonal matrix and we take the inverse, like in this case, or like in this case, and we take the transpose, so they are orthogonal, they have to be orthogonal, and the product of an two or more orthogonal matrices, that if A and B are two orthogonal matrices and if you do product, we will get the orthogonal matrix. And lastly, the determinant of an orthogonal matrix is always equal to plus minus 1. It's a very interesting thing. Determinant should be always a plus minus 1. Now, in the same notion, what we can say about unitary matrix is the inverse and the transpose of a unitary matrix is unitary. So you know that A inverse, so this is what it means, and the product of two unitary matrices is unitary. So similar to what has been observed in orthogonal matrix, the same is being observed in unitary matrix. The only difference is that the determinant of a unitary matrix is equal to 1, not minus 1. So where in the orthogonal matrix it can be plus 1 or minus 1, but in the unitary matrix it has to be only plus 1. Now based upon this unitary matrix, we have something called unitary transformation. So here it is basically a linear transformation, where if y is equal to ax, where A is a unitary matrix and x is a vector, and then this transformation is called the unitary transformation. So we can also put it in this way: if the matrix is unitary, then the linear transformation preserves length. Linear transformation, it preserves length. Another important aspect of matrix is something called rank. The rank of a matrix. Now, if the determinant of a matrix is not equal to 0, it is called a non-singular matrix, and if it is equal to 0, it is called a singular matrix. Now, a non-singular matrix is said to have, if it is a non-singular matrix, then it can have a rank R if at least it's R square minor. R square minor is non-zero. And if every R plus 1 minor exists. So let me explain what it is actually means. Say you have a matrix, you have a 3 cross 3 matrix, whatever it may be, A, B, C, D, E, F, G, H, K. Now this matrix, let's take this matrix as A, and A is not equal to 0. Now somehow, if we can find its minor, this is what is called an R square minors. It can be this minor, or it can be this minor. If these minors, any of these minors are equal to 0, then we see that the rank of the matrix is 2. Okay. Had it been a 4 cross 4 matrix, and had it been that say so whatever I, J, K, L, M, I, J, K, L, M, M, N, O, P, Q, R, S, T, U, V, W, X. The 4 cross 4 matrix, and if this matrix, say this is equal to P, if P is not equal to 0, but somehow we could find an R square minor. That means it can be any of 3 by 3 matrices here, which is equal to 0. It can be anything. Then we say that the rank of the matrix is 3. This is what is known as rank. Some more aspects of matrices. One of them is called an elementary transformation. That means if the interchange ith rows and jth rows, there is interchange of any 2 rows, ith and j, or ith column and jth, either row or column. That means say there is matrix 1, 2, 3, A, B, C, I, J, K, and say we replace these two. So let's say it is now A, B, C, 1, 2, 3, and I, J, K. Or we could have replaced this one. So in that case it would have been 1 AI, 3 CK, and 2 BJ. So here we have replaced the columns, here we have replaced the rows. So these are known as the elementary transformation. So this is the first step of elementary transformation, when the rows and columns are interchanged. The second type of elementary transformation is when we multiply every element of ith row or the jth column by vector. So every element of ith row or ith column by a scalar. Let's take the same example. Say we have matrix A, B, C, I, J, K, P, Q, R. So if we multiply any of the rows, say we take this row for example, multiply all the elements by K, K, K. Or if we have A, B, C, I, J, K, and P, Q, R, and if we multiply say middle column by K, so it's Ki, Kj, and K into K. So this is multiplying any of the ith row or the jth row by a scalar. This is another type of an elementary transformation. And the third type of elementary transformation is when the addition to the elements of the jth column by a k scalar type corresponding of the jth row. So if there is an ith column and we convert it into I plus scalar into j, into jth column. That means if we have a matrix say A, B, C, 1, 2, 3, and let's take it as alpha, beta, gamma, and PQR. This is a matrix. So this is the ith row. So if this is, now we change it by A plus K into alpha, B plus K into beta, and C plus K into gamma. So and this is another type of elementary transformation. So there's a three types of elementary transformation. Next is what we know as the equivalence. When two matrices are called equivalent, if A can be obtained from B by a series of by a sequence of elementary transformation, then we say that A is equivalent to B. And apart from that, there are some other properties of matrices. For example, adjoint of a matrix, and so for an adjoint, if A is a matrix given as Aij, and if alpha ij is called the cofactor of Aij, then adjoint of A will be all the cofactors A11, A21, and A alpha 1. Sorry, this should be alpha 2 1, and this should be alpha 1 2, like that, alpha nn. So this is what is known as the adjoint A, and by cofactor, we mean that alpha ij is equal to minus 1 to the power I plus j into m ij. So let's try to understand it in another way. What we have told is that cofactor ij is equal to minus 1 I plus j into m ij, and this mij is the minor, and the minor is obtained by striking off the ith row and the jth column and computing the determinant remaining from the image. So for example, let's take a matrix as 1 2 3 3 2 1 and 2 1 3. So this is the matrix, and we need to find the cofactor of, say, the first element. So this is Aij is equal to 1. So I plus, and this is actually A11. So the cofactor alpha 11 is equal to minus 1 to the power 1 plus 1, that is 2. So that makes it 1 square means 1. The interesting question is, what is mij? Mij is when we will strike off these two rows and columns, and we will take the determinant of this column. So determinant means 3 plus 2 minus 1. So determinant of this multiplied by this is 3 plus 2 5 is equal to 6 minus 1. So that makes it 5. So it will be 5. So the first term in the adjoint matrix will be 5. Similarly, the other terms. So that's how we will get the adjoint of the matrix A. Now, the matrix inverse of the matrix is related to the adjoint by the following way. A inverse is equal to adjoint A divided by the determinant of that matrix. Now, so these are some of the properties. The next thing that we would like to discuss about matrices is called characteristic equation. You can have a matrix equation in the following form. You can have AX is equal to lambda into X, where this is a vector. By vector we mean it is either a column matrix or a row matrix, single line of elements, and this is a full matrix, and this is a number, and again that matrix. So this is equivalent to an eigenvalue eigenfunction equation. So this is the eigenvalue. Now, to find out the eigenvalue, suppose a matrix is given in this form, we need to find out the value of lambda. Then what we will do, we will use the following way. So we will write that A minus lambda, so now put it in this way, AX is equal to lambda x. So AX minus lambda x should be equal to 0. So we take A minus lambda into I multiplied by x should be equal to 0. So by A minus lambda I means the diagonal element of A will be changed. So even one would be A minus lambda. The other elements will remain the same. So again A22 will be A22 minus lambda. Other will be the same, and A33 will be A33 minus lambda. This is what is A minus lambda I. And the system of non-homogeneous equation has non-trivial solution. It will have a non-trivial solution only if the determinant A minus lambda I is equal to 0. So we will get an equation based upon this, and then we will have to find the value of lambda. It can be more than one lambda. So there are lambda 1, lambda 2, dot dot dot. So all these are known as the characteristic roots, and or eigenvalue, whatever we. Lastly, there is something called diagonalization of a matrix. So if there is a matrix C, this matrix C is found such that the matrix A is diagonalized to S. That means if there is a matrix S where it is formed by C inverse A into C, then S will have characteristic roots as the diagonal elements. Have the characteristic roots as the diagonal elements. This is what is known as the diagonalization of the matrix.